Yes, I think you can start now. Go ahead.
Okay. Good afternoon, everyone. I am Yash Gawande. I am a 2021 batch mechanical fresher. Today, I will take you through the topic tree-based model. This session will be a bit different. It will be different than usual, but we are here to take you through this and make it a bit simple by taking different examples. Okay. I will begin with tree-based models. So first we will see what is a decision tree. Decision tree is a supervised learning algorithm which is mostly used in classification problems. Classification problems uh, are of two types. There are two type of input and output variables, categorical and continuous. The objective of a decision tree is to split the sample data that we have into pure sets. And these pure sets will have a common characteristic feature. I will explain this with an example. Let's say we have 30 students and 15 of them like to play cricket in leisure time and 15 don't like. And we have three variables. We will use these three variables to do split of the sample that we have. These three variables are gender, class, and height. Gender is basically boy or girl. Class is if the student is in class 9 or class 10. Height is if height is greater than equal to 5.5 feet, then it will be in one class. Otherwise, it will be in another. Okay. So I will split the data, that is 30 students, on the basis of gender. So you can see this picture. In the left part of the picture, I have done split on gender. Initially, we have 30 students in the sample, 15 of which we know that 15 play cricket. This decision tree-based models uses data which is labeled. That is, we know the output earlier. The correct output is known to us. For example, the output that 15 students like to play cricket in their leisure time, that is known to us. So I will do split on gender. Uh, by doing split on gender, I will get 10 students who are female. Out of those 10, two like to play cricket in their leisure time, and in the other one, which is the male, there are 20 students, out of which 13 like to play cricket in their leisure time. And after doing split on the basis of height, using 5.5 feet as the criteria, 12 students are there in the less than 5.5 feet criteria, in the 5.5 feet group, less than 5.5 feet. And in that, 5 like to play cricket in their leisure time. That is 42%. 42% is 5 by 12 into 100. And 18 students are there which are having height greater than 5.5 feet, and out of those 10 like to play cricket. Similarly, I have done split on the basis of class. Uh, in the 9th class, there are 14 students. In the 10th class, there are 16 students. Out of those 14 in the 9th class, 6 like to play cricket. And similarly, for the 10th class as well. So here I've shown how I have split the data, the sample that I had of 30 students on the basis of three parameters, that is gender, height, and class. So what a decision tree basically does is it splits the sample data that we have, and on the basis of the available variables that we have, and it decides the parameter which is doing the best split. Best split means all the people who like to play cricket should come in one group, and those who don't like to play cricket should come in another. Our aim is to find a parameter which will do split such that we will get all which are who like to play cricket in the leisure time in one group, and those who don't in another group. That is the ideal case which we want to achieve. Now I will take you through the types of decision trees. There are two types of decision trees, categorical one with categorical variable decision tree and another continuous variable decision tree. Categorical variable means that uh, like the example that I gave earlier, a student who like to play cricket or not in their leisure time, that is a categorical variable. That is, there are only two possible outputs. Either they like to play or they don't. That is yes or no. Uh, this can be similar. This is similar to either success or failure. So this is categorical variable and continuous variable. An example of continuous variable is income of a person. Income of a person can be predicted based on their age, occupation, and other information that we collect from them. So income of a person can have any value. The value of income can lie in any range. So it doesn't have specific two outputs. In categorical variable, there are only two outputs possible, either yes or no. But continuous variable may have different outputs depending on the information that we have. So these are the two types of decision trees. Now I will cover the important terminology related to tree-based algorithms. You can see this picture. This picture contains nearly all the terminologies. The root node represents the entire sample that we have. For example, the one with 30 students, which I had given earlier, that was the root node. And the root node undergoes splitting and it gives rise to decision nodes. Decision nodes are nodes which further split into subnodes. And after splitting a decision node, we will get terminal nodes. Terminal nodes are those which don't undergo further splitting. And in this picture, you can see that the nodes A, B, and C, these three nodes form a branch of the whole decision tree. So branch means a sub. It is a subtree. Okay, and after that, we can see that this the node A, is a parent node of nodes B and C, and B and C are the child nodes of node A. These are simple terminologies which are mostly self-explanatory. Other than that, there is one more term, pruning. In pruning, we remove the subnodes of a decision node. That is, we remove terminal nodes, which is exactly opposite of splitting. Splitting, we get terminal nodes by splitting a decision node. We get terminal nodes. In pruning, what we do is we remove terminal nodes, which are resulted from a decision node. So we are decreasing the number of nodes in pruning. I will elaborate upon pruning a bit later. Is everything clear till now? You can respond using any emoji. If it is also, you can respond in chat. I think it is clear. I will proceed. So we will look how does a tree-based algorithm decide where to split and which parameter should it use to split the sample that we have. So there are few metrics which we use to decide which parameter is best for splitting. I will take you through four metrics which are used. The first one is Gini index. Uh, this Gini index is used for categorical target variables, that is success or failure, which I explained earlier. And higher the value of Gini, higher is the purity of the terminal nodes that we get. And I had told you earlier that that is the ideal case which we wish to reach. We wish to have terminal nodes in the end, which are completely pure. That is, for example, the students who all are like to play cricket, they should come in one group. In Gini index, there are a few steps for calculating Gini index. Uh, we calculate Gini for each subnode and using a formula. The formula is p square plus q square. Here p represents the probability of success and q represents the probability of failure. We will calculate Gini for each subnode, and for calculating Gini for that particular split, we will take weighted average of Gini for the subnodes that we have, or terminal node you can say, and by taking weighted average we will get the Gini for that split. And Gini impurity is just 1 minus Gini. Referring to the example that I had given earlier, you can see this picture. It is the same example. 30 students is the sample that we had earlier. 15 like to play cricket, and we did. I'm here split on gender is done, and 10 students are there in the female and 20 in the male. And for that, I will calculate Gini value. I will first calculate Gini value for the female subnode. That here you can see that probability of success, that is probability that students play cricket in this subnode female is 20%. That is because two like to play cricket, so it is 20%. So here you can see it is 0.2 square plus 0.8 square. 0.8 is probability of failure, that is they don't like to play cricket. So we will get Gini for subnode female as 0.68, and similarly we will calculate Gini for subnode male. Here you can see that percentage who like to play cricket is 65%. That is probability of success that equal to P is equal to 0.65. So by applying the same formula P square plus Q square, you will get 0.65 square plus 0.35 square, and for subnode male you will get the Gini value. And then I will take weighted Gini, weighted average of these two subnodes. Here you can see that there are 10 students in the subnode female. So and total number of students in the entire sample is 30. So 10 by 30 factor will come before the Gini value of subnode female, and 20 by 30 will come before the Gini value of subnode male. So this is the calculation for it, and we will get Gini for split on gender. Uh, Now we will calculate Gini for split on class. Gini for split on class is calculated similarly. You just notice here that probability of success, that is they play cricket, is 43%. So probability is 0.43, and by applying the same formula, you will get Gini for class 9 subnode as 0.51, and here for class 10 the probability of success is 0.56, that is they play cricket, and you will similarly get Gini for subnode class 10 as 0.51. Then I will take the weighted average. Just a second. Then I will take the weighted average of the class 9 and class 10 subnodes, and by that I will get Gini value for split on class as 0.51. So by observing the Gini values for split on gender and split on class, we see that the Gini value for split on class is lower, and gender is higher. So hence the node will split. The node split will take place on gender, because I had told you earlier, higher the value of Gini, higher is the purity. Hence, we'll do split on gender. Now I will explain another metric which is used, which is chi-square. Chi-square also works on categorical target variables, that is success or failure, and higher the value of chi-square, higher is the difference between subnode and parent node. Notice this fact that we want pure terminal nodes. For that, there should be significant difference between the parent node and the subnode. Hence, higher the chi-square value, higher will be the difference between subnode and parent node, and it is more favorable for us. The steps for the formula is actual. This is the formula for calculating chi-square, and the steps are similar to calculate chi-square. We'll calculate chi-square for each subnode, each individual node, and we'll take using sum of all, we will calculate the sum of all chi-square of success and failure, and that is the value of chi-square for that split. In this table, I have shown the values. I have calculated the chi-square values for split on gender and split on class. We will first see this table. Uh, in the initial one, total in the female subnode, there are 10 students, out of which 2 like to play cricket and 8 don't. And in the male subnode, there are 20 students, so 13 like to play and 7 don't. And notice this fact that in the original sample that we had, there were 30 students, out of which 50% like to play cricket. So in the female subnode that we get, the expected is 50%. So 50% of 10, that is five people are expected to play cricket in the subnode female, and 50% of 20, that is 10 people are expected to play cricket in the subnode male. So by calculating the deviation by using this formula, actual minus expected square upon expected root of that, we will get the chi-square value for each subnode, and by adding all those chi-square values, we'll get chi-square for that particular split. Similarly, here you can see I have calculated chi-square for split on class. Here the expected who to play cricket is 50% of 14, and that is 7, and not in the class 10. The expected to play cricket is 50% of 16, that is 8. And by calculating chi-square for all the subnodes, we will get total chi-square for split on class. Again, you can see that for split on gender, the chi-square value is higher. So by using this metric as well, we get that the split should happen on using the parameter gender. Okay. Are these two metrics clear to everyone? If there are doubts, please ask. Please unmute or ask in chat.
Yes, there was a question in the chat.
Okay. How did we know that expected value is 50%? Okay. In the initial, in the sample that I had given, there are 30 students, out of which 15 like to play cricket, that is 50%. In the beginning, I had told that this is labeled data. So we know previously how many students like to play cricket. So here 50% like to play cricket, and we know that 50% like to play in the in the sample that we have. So the expected to play cricket in the female subnode or in the male subnode is also 50%. By that we know it is expected is 15%. Is expected to play is 50%. Is it clear? Okay, I will proceed. Now we'll look at the third metric, that is information gain. Please look at this picture. Which node can be described easily observing this image? By thinking upon it, you will get to know that this node C will require least information, because all the values that are present in that node they are all similar. Whereas in the node A, there are nearly 40% values which are blue in color, and 60% which are yellow in color. So there is disorder present in that node, in the node A. So least information will be required to explain node C, and lesser than that, slightly more than that will be for required for node B, and maximum information will be required for node A. So that is, the disorder is maximum in node A. Uh, this is similar to entropy, and here you can observe that C is the most pure sample that we have, and it has entropy equal to 0, and A is the least pure sample. It has highest entropy. So for splitting, after splitting, the lesser the entropy, better it is for us, because we want a pure node, pure terminal nodes at the end. So lesser the entropy, better it is. Now we'll look at the steps to calculate entropy. This is the formula for calculating entropy, and here P and Q represent the probability of success and failure. And by using this formula, we will calculate entropy for each subnode, and then we will take weighted average of entropy of the subnodes to get the entropy of the split that we are doing. Here I've shown the calculations for doing the same thing, and I am referring to the same example that I had shown earlier. The first picture that I had shown, it is the same example. So you can have a look at it. Uh, for the parent node, we can calculate it, the entropy. Here you can see that entropy for parent node comes out to be 1. That it is shows that this shows that it is a completely impure node. And we will calculate for a female node and male node, and after that we will take the weighted average and get the entropy for split on gender. These are the calculations for doing the same thing, and then again we will calculate entropy for split on class, and then again we observe that entropy for split on gender is lower than split on class. So we will do split by using gender as the variable, as the parameter. And these calculations are pretty easy. Just these P and Q are the probabilities. These probabilities are same as the ones that I had shown in the earlier metrics. You can just go through it once. Now we'll move to the fourth metric, that is reduction, that is variance, reduction in variance. So reduction in variance is used for continuous target variables. I had explained continuous.
Yes.
Okay.
Before you go on, there's a question in the chat.
What is the significance of total chi-square? Okay. Total chi-square just represents the uh, total chi-square just represents the difference that is there between the terminal nodes that we get after doing the split, and the difference between the terminal nodes and the parent node that we had. So it just represents the difference between the final subnode that we get and the parent node, that is the entire sample that we had earlier. If we use just the value of chi-square for only one subnode female, then that is not sufficient for explaining the entire split that we have done. We need to add all those values. Is it clear? I hope it is clear. I will proceed with the fourth metric. The fourth metric is reduction in variance, which is used for continuous target variables. And we will see that lower the variance, better it is. The split, the parameter which shows lower variance, that is used for splitting the sample that we have. Because you can see if we use this method by assigning values. One value is assigned for people who play cricket and 0 for not playing cricket. So if all people who play cricket are come in one group, then the value of x bar, that is mean, will come out to be 1, and x is also 1. So the variance will be 0 for that subnode. So hence we can say that lower the variance, better it is, better the criteria, better the parameter is. And this is the formula for calculating variance. It is just the standard formula that we use. X bar means the mean of the values, and x is the actual actual value, and n is the number of values which are present in that subnode. Uh, the steps for calculating variance are same. We will calculate variance for each subnode and then take weighted average for the subnodes that we have. And by doing that, we'll get variance for that particular split, and lower the split with lower variance, that is chosen for splitting the entire sample that we have. And after these are the four metrics that we generally use for splitting the sample that we have. Now we will look at classification and regression trees. I will just give I will just explain what are classification and regression trees. Classification trees are those which have categorical target variable or fixed target variable. For example, an example of this is who will or will not subscribe to a digital platform. And regression trees are those which have continuous target variables. And example for that can be predicting the selling price of a house, or predicting uh, the income of a person based on the information that we have. These are the two types of these are the two types of trees, that is classification and regression trees. And classification trees are used when we have the target variable as categorical, that is if the output for it is either yes or no. And regression trees are used for continuous target variables, which I had explained earlier. And CART just stands for classification and regression trees. That's all about classification and regression trees as of now. And after this, I will move on to advantages of decision trees. Decision trees are very easy to understand, and they are very useful when we have information, that is sample, when the sample is too large, that it has hundreds of variables, and it has the information is huge, and number of available variables are too much. Then these decision trees are helpful to uh, to decide which is the most significant variable, which will give the most pure terminal nodes. So these decision trees are very useful. And also there are few disadvantages to these decision trees as well. Uh, Overfitting is a disadvantage of decision trees. It may arise if the depth of decision tree is too much. Uh, Overfitting is one of the most practical difficulty, and for overcoming this difficulty, there are few methods. I will explain those methods. Overfitting can be prevented using few ways. The ways are as follows. We can set the uh, maximum number of features used for doing splitting. Also, we can set the minimum number of samples that should be present in a particular node for that node to undergo splitting. That is this one. And minimum samples that should be present in the terminal node, that is also one condition. And we can set a restriction on maximum depth of that decision tree. That will also help overcoming overfitting. And Other than that, there is one more. Uh, we can also use maximum number of features that that we should consider while splitting a node that we have. By using this 4 or 5 tech, methods, we can set up constraints on tree-based algorithms, and that will help to overcome the problem of overfitting. I will explain a method of called pruning, which I had mentioned earlier. In pruning, what we do is we remove the terminal nodes, and we go on removing the terminal nodes. We first check what is the information gain that is there from a particular split. Let suppose a split is giving us -10 information gain, and the next split is giving us +20 information gain. So by doing those two splits, we are getting a net gain of +10. And uh, by using in pruning, what we will do is we will th think about what is happening further, and on the basis of that, we will decide whether we should remove that particular terminal node or not. What a simple decision tree will do is it will see -10 information gain is happening, so it will stop over there only. In pruning, we will see a bit further, and since we are getting +10, uh, we will continue. So this pruning is a good technique, and these are the terminologies which are associated with decision trees. Is everything clear till now? After this, I will explain how to build a basic decision tree. Are there any doubts? If no, please type it in chat or respond with a emoji.
There was a question in chat.
Okay. Uh, okay, fine. I will explain how to build a basic decision tree. Here I have just imported NumPy and Pandas, and I had sent the two CSV files that I'm using in WhatsApp groups. Please check out them. And in this, in the data that we have, what we wish to do is we have data that is if blocked arteries are present in the patient, if chest pain is there or not, if blood circulation is good or not. This is present. One means blocked arteries are present, and and also we also have if heart disease is there in that patient or not. So by using three uh, these these three parameters that we have: blocked arteries, chest pain, and good uh, and blood circulation, we wish to predict if heart disease is present in the patient or not. For that, we'll use a decision tree, and first we will calculate. We have a sample. For that, we wish to decide which is the best parameter for splitting, and for that we will use Gini index as the metric. And after deciding which is the best one, we will do splits. And after doing splits, we will do predictions if heart disease is present in that patient or not. So let's begin. Uh, first, we first I have calculated Gini index for the parameter blocked artery. Here in this image, you can see in the sample data that we have, if blocked artery is present in that patient, then there are 215 patients who have heart disease in uh, when they have blocked artery. And if they don't have blocked artery, there are 292 patients who have heart disease. So I have just shown in this image, and by using these values, we will calculate Gini index. Gini index is calculated for using the same method I had described earlier. That is, And I had also mentioned that Gini index is p square plus q square. Here I have just used the other formula, that is 1 minus p square minus q square. That is the Gini impurity that had shown you earlier. Gini impurity is just 1 minus Gini index, and by using the values that we have over here, we will just calculate the Gini index for this, and the Gini index comes out to be 0.499 for the parameter blocked artery. And after that, similarly, I will calculate Gini index value for other parameters that I have: chest pain and blood circulation. This is the code which represents the calculation of Gini index. I will explain this code. Entry in this, this is the formula, that is 1 minus p square minus q square, and count 1, count 2, count 3, and count 4. Count 1 is represents the value where entry 0 is equal to 1. That is the blocked artery is present and heart disease is also present. So 215 is the value of count 1, and count 2 represents entry 0 is 1 and entry 1 is 0. Entry 0 represents heart disease. Entry 0 represents blocked artery, and entry 1 represents heart disease. So entry 1, this count 2 represents the value 227. And similarly, count 3 represents 292 and count 4 represents 266. By using these values, we will calculate Gini value for the first node that we have, and uh, for the second node also that we have. By using similar formula, we will calculate Gini value, and then this is just the code for calculating Gini value for the parameter that we are using over here, which is blocked artery. By using similar code, we will calculate Gini value for the other parameters that we have, which are chest pain and blood circulation. By seeing this Gini index, we will see that blocked artery is the best parameter. Uh, Gini index is least for blocked artery. So we will use this for doing the first split on the sample data that we have. So we will split the data on the basis of blocked artery parameter, and this is just the code for splitting the data. And after that, there is not blocked data and blocked arteries 1. So after this, we have to decide which is the best parameter for splitting the not blocked data that we have and blocked arteries 1 that we have. For the not blocked, again we will calculate Gini index using the parameters chest pain and blood circulation, using the same similar code that we had earlier. And here this in this command, we are just going through the not blocked values that we have, and c comma 1, just c represents the rows and 1 represents the first column, the index of the column, the second column, that is chest pain. And after that, and c comma 3 represents the value that is present in the heart disease column. This value which I had shown earlier, these values represents the third column. So by doing this, we will calculate Gini index values for chest pain and blood circulation, and after that, we observe that in the blocked data that we have, then in the non-blocked data that we have, the Gini index value is yeah, the blood circulation is the best parameter for it, and the Gini index value is least for blood circulation. So we will use that, and for block data, again, we will calculate Gini index values. And for block data, we see that the best parameter is chest pain. And by using these parameters, we will split the initial sample that we have. First, we'll split using blocked artery. And after that, you will use chest pain for uh, the blocked artery is one. And when blocked artery is not present, we'll use good blood circulation as the parameter. This picture represents if heart disease is present. This yellow, the leftmost yellow cell represents when blocked arteries and chest pain both are present. There are 135 patients who have heart disease and 121 don't have heart disease. So uh, these values represent the number of patients who have heart disease and who don't have. And after that, we have to make predictions using these values. Here you can observe that there are in the leftmost cell there are 135 patients who have heart disease and 121. So there are more number of patients having heart disease in when their blocked artery is present and chest pain is also present. So we will assign yes value to this, that heart disease is present. And here you can observe there are 82 and patients who have heart disease and 104 don't have. So we will assign no value to this. By doing that, you can see this uh, heart disease. I have written true value over here. That is, heart disease is present over here, and false when blocked artery is present and chest pain is not present. So this is the splitting that I have done using the sample that I had, and this is the code for it. The code basically represents if blocked arteries is present and if chest pain is present, then heart disease predicted value should be 1. That is, there is heart disease. And else, that is, if uh, chest pain is not there, then heart disease predicted value is false. It represents this, that is, heart disease is not there. And if blocked arteries are not present, then this line represents if good blood circulation is there, uh, then you assign heart disease predicted value as 0, that heart disease is not present, and else it is present. This is the representation for it, that heart disease is not present when blocked artery is not there and good blood circulation is there. So this is the picture representing the whole split that I have done on the data that I had. And these by using the algorithm that I have the tree-based model that I have developed, uh, these are the uh, these are the data values that I had earlier. This is the test. Uh, these are the values which are present in the test CSV file, and these are the predicted values that I'm getting by using this tree-based model. So you can observe that here heart disease originally was not present, and my model predicts that it is not present. In 80% of the cases, you can observe that my predictions are correct using this tree-based model. And by using sklearn library, I've just printed the accuracy of this tree-based model, and it comes out to be 83% accurate. And this is a very simple decision tree. It is easy to understand, and it gives good predictions. I have kept the depth of the decision tree to be less for easier understanding. Are there any doubts? Yes, we can use other metrics as well. Uh, yes, we can use the other metrics, and by using other metrics as well, other than Gini, you will get similar results. Because earlier I had shown you by using the same example for all the metrics that the split on gender was the best. So for by using other metrics as well, you will get the same results. All the metrics will take you to the same conclusion. For increasing the accuracy of this, uh, you can you can train the model more by increasing the depth of this decision tree and using more data by training the model more and increasing the depth of this decision tree. It will learn more, and by as it learns more, you will it will make better predictions. So by increasing the depth of this decision tree, uh, it will definitely help to increase accuracy, but you need to be careful. If you increase that depth too much, it will lead to the problem of overfitting that I had mentioned earlier. So there will be an optimum value of the depth that you need to check by doing experiments. So this is all for this is the basic introduction of tree-based models, and I have shown you the implementation of a simple decision tree. Uh, i- if if there are no doubts, I am done with my part. Over to you, Shankar. I will stop presenting.
Are there any doubts on this part?
You can unmute and ask as well.
Guys, please unmute and ask if you have any questions. It's a very different topic from what you've discussed so far. So yeah, definitely. We can have a 5 minutes break. This was a long part. So Archish, if that's okay with you, we can have a break.
Yeah, yeah, sure.
Okay.
Yeah, so maybe we'll start at 2:57, I guess.
Yeah, okay. Can we start now?
Yeah, cool.
Okay. So, can you all see my screen? Can you hear me? Just confirmation.
Yes, you are audible. And screen is also visible.
Okay then. So, building up on what Yash had discussed in the previous part, so you can see how decision trees just collect small information from the data and use it to predict the correct output. So, as someone asked very well, how would we increase the accuracy of such a model? So, as Yash said, one method would be to increase the depth of the tree. But if we keep increasing the depth of the tree, we will not be able to accommodate all the features which contribute to the output. In that case, we would need multiple trees. Each tree may encompass a certain number of features and help us predict the correct output. So that is what ensembling is all about. And ensemble methods are different algorithms that combine such different trees in different methods and give us a better output with better accuracy. So first, I've just described the basic principles of machine learning. As you all already know from the previous sessions, there is supervised learning where there is a given input and output. And then there is unsupervised learning where we make an assumption and try to classify data based on their similarities. And then there is reinforcement learning, which consists of assigning a loss function or a cost function, which says if the model performs in the wrong way, you just tell it mathematically that, hey, you don't do it this way, you do it the other way. And then it repeats the process and improves its accuracy. So mostly we'll be doing supervised learning here. And of course, there's regression and classification. And then there is a decision tree method, which usually deals with classification problems. And among the in the decision tree part, we have a cart algorithm, which is basically classification and a regression tree. And Yash explained how classification tree is used for classification problems, and a regression tree is used to predict a more continuous output. That is, there is no fixed range for the output. It can give any answer. And there are different ways where the node is split. And as Yash explained again, I'll just go through whatever he did. So that'll be a good recap of decision trees. There's Gini impurity, and there is variance descent or variance decrease. And then there is information gain, and then there is entropy. And here is just a figure I have just pasted here because I thought it will help you understand how information gain is used to split the node. This is just for one simple tree where there is only one split. If the sum of information gain of the child nodes is greater than the parent node, then we split the node. Of course, if you want to increase the depth of this tree, we will do it for each of the child nodes subsequently. And of course, information gain for each node depends on the features and the data we have provided. So is that clear so far before we get started with our content?
Yeah, Shankar, could you also share the notebooks and data with them on the groups?
Yeah, 1 second. So I'll just stop sharing before 1 second. Yeah, so I hope my screen is visible. And in the WhatsApp group, I have shared this notebook and the corresponding CSV files, which I'll be using to implement my model. So hope you all follow along. So basically, there are different types of ensemble methods. The first one is what we call bagging. And in bagging, there is a more refined version of bagging, which is called random forest. And we will be going into that in a bit more detail. And then there is standard bagging decision tree, which I will also be implementing in this lecture. And then there is boosting, which is another ensemble technique. There are usually three most commonly used types of boosting. We have gradient boosting, and we have adaptive boosting or AdaBoost. And then we have XGB boost, which is basically extreme gradient boosting. And it is done usually with parallelized computing to increase the speed. Now, I hope this is clear so far. So we'll go into bagging. Basically, bagging is called bootstrap aggregation. Bootstrap, which I'll explain later, and aggregation is just combining different models. So first I'll have to explain what is a bootstrap or bootstrap data. So let us say I have 10 data points. I will try to create a random data set with the same number of elements, which is 10 here, but repetition is allowed. That is called bootstrap data. So to explain what is bootstrap data, um, I'll just open my notepad here. Let's say I have 20, 20, 30, 40, 50, 60. Now there are 6 elements here, but I'm creating a data set. I'm just randomly picking elements from this. So I'll just write it as 20, 20, 20 throughout. This is a bootstrap data set. Another possible bootstrap data set would be 30, 30, 30, and so on. You could also choose the same data set again. That is also possible. It's just completely random. Purpose of this is to take all possible combinations of the data so that it remains invariant with respect to distribution. By invariant with respect to distribution, I mean that even if you shuffle the data or even if you like the features you extract from the model should not be dependent on how the data depends with each other. So first I'll have this figure right here. It explains clearly on how bootstrap data is used to compute the model. So we have an initial data set and I create n such random data subsets of the data, which I did here in this notepad. And then there are a bunch of trees. We'll call them M trees or so, whatever. And each tree uh, takes in this data set and then processes it to give an output. Now each of those trees will be constructed by us. Usually we have certain libraries which do it for you. But as Yash explained, each tree is constructed like how he did it. So we have n different outputs obtained here, and we aggregate those results. Now there are different ways to aggregate the result as well. There are two types. Usually there is majority voting, and then there is mean averaging. In here, we will be doing something called majority voting in a classification problem. Majority voting is just seeing which output has the most number of times occurred. Like, let's say, you just choose the output which you get the most number of times. That's it. That is called majority voting, and that will be our final prediction from the model. Now, we'll be going into something called random forest. Forest is just a collection of trees. The size of the forest depends on its user preference. So random forest is a random collection of trees which process random subsets of data. Now the difference between a regular bagging model and a random forest is that random forest splits the features as well. Whereas in a regular bagging model, as we saw here, all the features will be used to determine the split of each node. Whereas in random forest, you will choose a certain subset of features as well. Let us say there is a person's, you just want to check whether a person is obese. A lot of factors which come into play: his age, his intake, is exercise, etc. Now, a regular bagging model would take into consideration all these features and decide the split at each node. Whereas a random forest, you can, for one tree, it will be something like age intake. The second tree will just be intake. Third tree will be exercise, age, etc. So you can observe the variation of the output with respect to each feature. That is why random forest usually gives a more correct output than a regular tree. So basically, it implements a level of differentiation. That is because it will be split on different features. So there are certain steps to implement a random forest. Our first step, which we already discussed, would be to create a bootstrap dataset. By dataset, I mean you can create n number of datasets. So I also explained what is a bootstrap dataset. If there are any questions so far regarding this step, you can post it in the chat. I'll wait for like 1 minute or so. Are there any questions?
Can you briefly explain the that dataset part again?
Bootstrap dataset.
Yeah.
Okay. It would be better if you stay on mute while I walk you through this. Just tell me, there are 10 inputs given to you, okay? Let's say age, and then there's 10, 20, 50, 60, 20, 20. You can see my notepad, right? Hello?
Yeah, it's visible, but the guy's muted himself.
Yeah, it's fine. So basically what you need to do is create a data set with the same number of data points, but replication is allowed. You just randomly select data points from it. You can choose 10 throughout, or 10, 20, and then 50 throughout, or 10, 20, 50, and then 60 throughout, whichever works for you. You just need to create n random samples from this data set with same number of data points. Is that clear, or does it require a little more explanation?
Yeah, no, I got it. Okay, thank you.
Yeah, okay. So we've created a bootstrap data set and hope that's clear with all of you. I've just shown an example of how bootstrap data set would be. We'll have to choose 4 data points here. This is the input and output columns given to us. We choose 4 data points. And in my case, I'm just choosing the first row thrice, and then the third row appears once. So it's just 20, 50, 20, 50, 20, 50, and 30, 60. Yeah. So step 2 would be to create a decision tree using the bootstrap dataset, which we obtained from the previous step. But we'll select a subset of parameters which influence the output. And now we'll have to build a decision tree, which is what Yash did. I'm not going to explain how you build a decision tree here because it was already covered in the previous part. But let's say you just build a decision tree. In the end, you will come out with some output, right? So you store that output. And now you do step 1 again for as many bootstrap data sets as possible. And now you've compiled all those outputs. You just choose the output which you get the most number of times. And that will be your desired output. And there is something called out of bag error. So I'll be explaining what is that. So you're just randomly choosing samples, right? When you're randomly choosing samples, statistically, when you have a large number of samples, you tend to miss out on some number of samples. Typically, you get around 1/3 of the sample that doesn't appear in the data. So you'll call those samples which don't appear in any bootstrap dataset as out of bootstrap or out of bag data. You can call it whatever you want. Now the number of, since you got the model, that the model is basically the collection of all these trees. So what you do is you take one of these out of bag samples, run it through all these individual trees which you found out, and then you check whether it gives you the desired output or not. As I told you already, this is a supervised learning. So which means we'll have the desired output already with us. So if it is correct, then you proceed. If it is wrong, we'll count how many wrong samples are present. And we'll call that error as out of bag error. Out of bag error is a fractional error. That is the number of out of bag samples that give an incorrect prediction when run through the given model. Is that clear? Or does anyone have any confusion? Make sure you understand what is out of bag sample. That's your first step. And what you do with the out of bag sample and what is out of bag error. These three things, I hope you got it. No questions? Okay, if there are no questions, I'll proceed. There are no questions, right? Yeah, okay, then I'll proceed. So this is just an implementation of a bagging classifier and random forest. So here you can see on the left side, I've imported the CSV file. I've shared it in the WhatsApp group also, so you can follow along if you want to. So I'm importing the pandas, which is used for data manipulation. I'm reading it. All this is fine. I'll just showing you what columns are here. So there are a bunch of columns: year, month, day, temp1, temp2, etc. We're just predicting the temperature here. So yeah. So what I'm doing here is I'm splitting the train data into train data. I'm given the data, splitting the given data into train data and test data. So train data is what we'll be using to create those bunch of trees which we saw in that figure. And the test data is the data which will be running through those trees and seeing how well the model performs. And that can be done using the scikit-learn library. So scikit-learn model selection, train test split. The data is the data frame which we have imported, temps.csv. We have labels and test size is 0.25. So 1/4 of the data set will go to testing. And you may notice this random state 42. You can give the value as anything here. It can be random state 0 or random state 1. But the random state value is just used to ensure that the train data and test data stay as such. Like there is no exchange of data points between them. Even when you recompile it, you'll get the same set as train data and test data. That's it. That way you can ensure uniformity. Yeah, so here using the sklearn library in the ensemble part, we have the random forest regressor. And then you have a decision tree classifier and a bagging classifier. So basically I'm creating a structure which is called tree. Yash did the tree manually, right? Like he created the tree using if-else conditions. But there is a library in scikit-learn which can create a tree based on how we want it to. So tree is equal to decision tree classifier. Criterion is entropy. You can also use information gain, or there are certain other parameters as well, like variance, descent, etc. And then random state 42, max depth is none. So which means it's without pruning. You cannot cut the length of the tree. And I'm also defining bag, which is a bagging classifier. Base estimator is tree. So what is base estimator? It's just the first unit, the tree. And then the number of estimators we want. I'm choosing 500 trees here. And then OOB score is the out of bag score, which we just saw. And this I'll explain later, these three parameters. So now that I have created a bagging classifier, I will fit it with the train data and train labels. And I'll print the out of bag score as well. And just mathematics here, I'll just print the final error, which we get from this. So out of bag accuracy in the temps.csv file is 0.107 and test accuracy is 0.09. And we get the accuracy in percentage is 92.7%, which is actually pretty good since we have 500 trees. So can someone guess how much the accuracy will be if I make this number of trees as 1,000 or 5,000? Anyone? Hello? Just
The
take a random
accuracy will
guess.
increase.
That is what you would normally expect. But if I make the number of trees say 1 million, does that mean my accuracy will go to 100%?
No, then it will be like it'll go lesser because it overfitting some sort of.
Yeah. You don't want the model to overfit, right?
Yeah.
But what you're saying is when it overfits, the accuracy will go down.
No, I mean then by if you increase number of estimators, the like it will be almost like an overfitting case, and so any sort of prediction that one makes will be off the accuracy in those cases.
Yes, but yeah, that would what would happen in case of regular regression. But in the case of bagging, since we have certain number of trees which read each feature and give us the correct output, after a certain point of time, when we increase the number of trees, those trees would not be able to read any new feature from the data. So they would just be keep reading the same feature which was already read, and it'll give the same accuracy actually. Unlike polynomial regression where the curve is always trying to fit the model, in decision trees, you can have redundant trees as well. That is useless trees, which do no extra work. Do you understand what I'm trying to say?
Yes.
Well, let me just run this for you. Maybe you'll understand. It'll take some time, I guess, since it's 5,000 trees. This is just a regular bagging classifier, by the way. Random forest also bootstraps the features along with the dataset. So that implementation of random forest we'll be discussing in a while. Yep. So you can see, right, what the accuracy is. It's still 92.59%. There is no increase. So what does this mean? Feel free to unmute and tell me. Even if it's wrong, don't bother. We just want the session to be interactive.
Like if there's like a threshold of number of estimators after which there's like no effect of it.
Yeah, exactly. So the number of estimators, when you keep on increasing, they just become useless. They'll be doing the same job what some other tree had done before. So what's the point, right?
Yeah.
So in the end, your accuracy will cap at certain value. So that's why people prefer using bagging. It prevents overfitting. Unlike regression where the model just keeps on fitting itself till we get 100% accuracy. In bagging, overfitting is prevented in such a nice way, actually. Hope this concept is clear to everyone, why bagging plays such an important role in machine learning.
Yes.
Okay. So here I'll just be implementing random forest regressor. It's actually very simple. You guys can understand it, but I'll just be going through it. So I'm basically passing the random forest regressor with 1,000 trees. Okay, that's a bit high to RF, and I'll fit train features and train labels. Basically, input train and output of train. And then predictions can be done using the predict command, which is available in scikit-learn as well. And error is I'm just using one absolute difference between the predictions and test labels as my metric. And I'm finding the mean of those errors. I get 3.87. So the error percentage will be 3.87 by the number of test labels times 100. And you subtract that from 100, you'll get approximately 93% accuracy, which is higher than the bagging classifier, but the bagging classifier also does a good job. Maybe if I increase the number of trees, it may cup at a higher percentage. Why don't we try it out? Yeah, so it goes till approximately 94%. So it probably cups at 94%, even if I increase the trees. Now that I hope everyone has understood why we use bagging, what is bagging, and what is random forest. Are there any questions? Feel free to ask. No questions? I can't see the chat, so I don't know if there are any questions in the chat. Okay, if there are no questions, then I'll continue to boosting. Please stop me in the middle if you have any question. Okay? So now that we saw bagging, basically we're just randomly shuffling the data, splitting it into n parts, constructing a tree for each of those n parts, getting the output, and we'll choose the output which occurs the maximum number of times. That is bagging, to sum it up in like one paragraph. Now, what is boosting? It's a sort of similar technique, but it's a bit unique and actually much more interesting. So we'll be using something called a weak learner. A weak learner is usually a stump, a tree with just three nodes, basically one root node and two child nodes. That's called a stump, and we call that a weak learner. Why do we call it a weak learner? Because since the depth of the tree is very less, we won't be getting the correct output. So what boosting does is basically we combine a set of weak learners to a stronger learner, and we minimize the training error. And combining these weak learners is what boosting is all about. And something interesting about boosting is we take in the errors of the previous weak learner and make sure that the subsequent weak learner is more accurate. That is, tries to correct its mistake. And there are different types of, this will become much more clear once I explain the ADA boost. And there are different types of boosting: adaptive boosting, gradient boosting, and extreme gradient boosting. I'll just be explaining ADA boost today because that is the most commonly used one. And it's less mathematically rigorous as well. So what ADA boost does basically, okay, I'll just start with a simple data set. Let us say I have age, and then I have weight, and then okay, we'll choose something else. Temperature, uh, country, and then we have, okay, I don't know what data set to choose. Maybe age, country, company, and then income. Yeah. And there's a lot of data sets here. Yeah. So what I'll initially do is I'll assign a weight to each of these data points. Let us say there are n data points. So weight of each of them will be n, 1 by n. 1 by n, which is the probability of choosing that data point. So I hope it's clear so far. I'm just assigning a weight for each data point, equal weights initially. 1 by n, 1 by n, and so on. So now what I'll do is someone's unmute, please. Okay. So I have a stump, which is 3 node tree which takes in all this data set, the entire data set, gives out an output. Now there must be certain error metric because it's supervised learning. If the error is less for that particular stump, we like that stump, and we would like to have more such stumps in our model. If the error is high, we want to change the stump. That's our first step. The next step would be we don't want that stump in our model because that's just giving us bad results. So if the error is bad, or error is high, we don't like this stump, and we would like to remove it or give less weightage to that stump in our model. Is it clear so far? Just very simple logic, okay? We have a stump, we have the data set, you pass the data set through the stump. Whatever prediction it gives, a stump is basically a small decision tree. So whatever prediction it gives, if the prediction is correct while training, we'll keep that stump. That is, we'll give it high weightage. If the error is high or if the stump does not give the desired output, we don't like that stump, so we'll give it lesser weightage in our final model. Okay, so now that I've explained what our basic idea is, so the step one to creating an error boost classifier is creating the root stump of the model. That is the first stump. This is done by choosing the best feature which splits the model nicely. In the case of Yash's explanation, we saw that gender splits the samples nicely. So we'll choose gender. And we will try to pass all the data points into this root stump and see what decision it gives as the output. So the total error for the stump is the sum of weights associated with the incorrectly classified samples. So let's say I have this data set here. I'm passing each of these data points into the stump. And let's say the first one gives correct output. I have 5, right? So here, just 1 by n, 1 by n, 1 by n. So there are 6 data points here. 6 or 5? 6, yeah. Correct, correct, incorrect, incorrect. Yeah, let's say incorrect again. So I have 2 out of 6 samples initially. I have these, this is the prediction I've got from the stump. If it is correct, I won't add the weight. If it is incorrect, the error for that particular stump is sum of incorrect weights of individual incorrect samples. So these 4 were predicted incorrectly. I'll add 1 by n 4 times. So it will become 4 times 1 by n. Note that the weights will change after each stump is processed. Okay, that's why I'm not writing it as 4 times 1 by n. I'll write it as W1 plus W2 plus W3 plus W4. Any doubts so far? Please ask questions if you have doubts. It's actually very interesting. So, any doubts?
No.
Okay. Yeah. So, as I said, we'll assign a weight for each of the stump. The weight will tell whether we want the stump in our final model or not. That is, you can't definitely say it won't be there in our model, but if the weight is high, it will have a higher say in our output. And if the weight is lesser, it will have a lesser say in our final output. So weight of the stump is directly proportional to the amount of say it has in the final prediction. I'm explaining it very intuitively so that you guys don't be confused by all this math stuff here. So the weight is calculated by this function. You can actually use other functions which vary as well, but This one is very unique and it's kind of nice because you can see this graph. When total error for that stump becomes 1, basically we don't want that stump at all. Or let's say the total error is 0, right? In that case, what would be the weight? We'll have a higher weight, plus infinity, which is never possible. Total error can never be 0. But yeah, as total error tends to 0, the weight will tend to infinity. As the total error tends to 1, the weight will tend to minus infinity. Because log 1 is log 1 minus 1 by 1, right? That case will become log 0 by 2. And log 0 tends to minus infinity as value tends to 0. And when total error is 0, this value tends to infinity, the brackets. So log infinity is approximately infinity. So basically, when the error is less, we will give it more weightage, and the error is high, we will give it less weightage. So this is something you all should understand intuitively. This graph is kind of nice. Now, similarly, we take another parameter and we will calculate the weight of the stump in the final model. That is fine. Like for each parameter also you can do it. Let's say there are four parameters which influence. Okay, 3 here: age, country, company, and income. There are 3 parameters here. You can do it for 3 separate stumps. Now, what if a particular sample has been classified incorrectly? That is, it does not give the desired output we want during training. I should take some um, corrective measures, right? That's what AdaBoost does. So basically, it adjusts the weight of the sample as well. That is, after finding the error and after defining the weight of that stump, it changes the weight of the samples. If the sample has been incorrectly classified by a stump, we do this. The new sample weight is original sample weight times weight e power weight of the last stump. And you can see that e to the power the weight is always greater than 1 because weight is always greater than or equal to 0. So this part is always greater than or equal to 1. So the new sample weight is greater than or equal to the original sample weight. That's all you need to understand. Forget this function, okay? Now I'll show you, after I explain this, I'll tell you why these weights are changing and how it affects our next term. So basically, if a sample has been incorrectly classified, we increase the weight of the sample. And if the sample has been correctly classified, naturally we should decrease the weight of the sample. And once we decrease the weight of the sample, we'll do it by this. And of course, the sample weights might not add up to 1. So we should obviously normalize it. That is weight divided by the sum of all the weights of all the samples. So that will give a normalized weight. So let's say weight was 1 by n here. It was 1 by 6, right? So it 1 by 6. Weight of those first 2 samples will become 1 by 6 times e to the power the weight of the sample, which was 4 by 6, I guess. 4 by 6, 1 by 6 times e to the power 4 by 6. Oh, this is correctly classified, right? So it'll become negative. And for the remaining ones, it'll just become e to the power plus. I hope that's clear. I'll tell you why we're changing these weights. And now we normalize it. Because we want the weights to be probabilities. Vary from 0 to 1, that is. We normalize each weight. That can be done by W by sigma W. That's it. Yeah, so I hope that's clear. Any questions here? I'll pause. This part may be a bit confusing. If there are no questions, I'll continue. Are there any questions in the chat? Okay. Fine, I'll proceed. So obviously you people will ask their weights. So shouldn't they add up to 1? That is why we normalize it. Now, this is the most important part. How we calculate the subsequent term based on the normalized weights. In theory, we could use the weighted Gini index for giving more emphasis to the incorrect sample in this term. Okay, but what you want to do is make the next term process data which has more number of incorrect samples so that it would be able to train the incorrect samples in a correct way. So create a new data set where the frequency of incorrect samples in the previous term is higher than the correct samples, right? Does that make sense? It's very intuitive as well. Like, say you do something wrong, but you want to correct it, you focus on that area more, right? Just like that, we create a new data set where the frequency of incorrect samples in the previous term is more occurring than the correct ones. And how exactly do we do this? Well, it's actually quite simple, but it's a very elegant method. So let's say our new weights is something like 0.1, and we have 0.2, 0.3, 0.3, 0.4, 345. Is this even? Oh, okay, it's not right. 0.2 and 6. Okay, this doesn't make sense. I'll make it 0.1 and 0.2 as well. I just want them to add up to 1. Okay. Yeah, and 0.1 at last. So what I'll do is I'll calculate the cumulative frequency. I'll assign ranges 0 to, initially I'll have 0 here, 0, now 0 plus 0.1, which is 0.1. Now I'll add this 0.1 to the free weight here, which is 0.3. Now it becomes, you can all predict what it is. It's just 0.3 again, so which is 0.6. And now it becomes 0.7 and so on and so forth. Basically, we'll just set ranges 0 to 0.1. We'll take the previous sum 0.1 to 0.3, 0.3 to 0.6, 0.6 to 0.7, 0.7 to 0.9, 0.9 to 1. These are the ranges which we have formed now. Now in very big data systems, there'll be approximately like 50,000 data points, right? So obviously there'll be some 50,000 such ranges. So what I'll do is, let's say there are 6 data points. Let's say there are n data points. N data points. I will randomly choose n numbers from 0 to 1. Okay. And if that number lies between a particular range here, I will add that particular element corresponding to that range to the new data set. That will ensure you see that the range of each of them is actually just the weight of that sample. So which means that there is a higher probability that I choose 0.7 to 0.9 than 0.9 to 1 when I'm randomly choosing it, right? So obviously in a very big data set, when I choose numbers like this, I'll most likely have more 0.2s than 0.1s. So probably the new data set will be something like 0.2 and then you have 0.2 again, and then you have 0.3 maybe once in a while, and you have 0.2 again, and then 0.1. This will ensure that the new data set, it will not ensure obviously, but when you take a very large data set, this is what actually happens statistically. So when you choose a large number of points, you can see that the number of 0.2s is higher than 0.1s. So that will ensure that the 0.2s, the data set corresponding to 0.2 is trained more efficiently in the next term. Okay, I think this part I've explained. So if you guys have any questions, please stop me here. This part can be a bit confusing.
No questions.
No questions, seriously. Please post your questions on the chat as well if you have any more questions. Okay, so if there are no questions, you understand, right? It's a basic summary of how AdaBoost works. I'll just give that. Maybe you guys will now properly understand what happens. There is a stump, there's a data set, process the data step, process data set using stump. If stump gives less error, assign it more weight, which subsequently implies it has more say in the model. If stump has more error, assign it a lesser weight. And we can say it will have lesser say in the final model. How will the say be determined by weight? Basically, you're going to find a weighted sum for determining the output, unlike the previous case where we use majority voting. I'll tell you, I talk about that. Now, after each process we've done, we've processed one stump and we've assigned it a particular weight. For correct samples, is weight. For incorrect samples, increase the weight, normalize the weights, create a new data set where frequency is proportional to the weight in previous term. Weight after previous term, actually. Previous term processing. Now repeat. After we have created all these stumps, let's say there are some 1,000 stumps. So here comes the interesting part, testing phase. We will have, let's say stump 1 takes in the data, process it, gives output. Similarly, stump 2 takes in the data, process it, gives output, etc. And stumps. And the output is defined as the weighted mean of the output of each stump. Basically, those stumps which had higher weight after training the data set, those will have a more say in the model. That because it gives lesser error, right? So we saw that it gave lesser error while training. So we would like to use the output given by that particular stump more often in the model. So that is why we use this weighted mean here. And we will print that as the final output. Of course, there will be errors, which you'll see. So this is the implementation. Implementation is very easy. You never get to see what is happening inside actually. But yeah, This is essential when it comes to practical life. So you can see how scikit-learn has a standard library called the ADA boost classifier. And we just do the same thing. What we did for the random forest, we split the data into train data and test data. We will pass AdaBoost classifier to an object. ADA boost is equal to sklearn.ensemble at AdaBoost classifier. And here I've given it 100 estimators. So basically 100 such stumps. You should know what these estimators mean. There are 100 such terms which are processed sequentially. And then we fit the AdaBoost over train data. And we predict the outputs using the predict command. And we find the error. And you can see how well this works. You get 100% accuracy here. And usually that's not possible. Probably when, let's see, how about 50? Let's see what's the accuracy. It's still 100. How about 10? It's still 100. So what does this mean? It obviously means that the data is being overfit, or because I have split the train data, the original data set into train data and test data. Possibly the test data may also have the same features as the train data because it is from the same data set. So it becomes much easier to predict the final output. There are two possible cases. But as you can see, boosting never tries to prevent overfitting. It only tries to increase the accuracy. Unlike bagging, where overfitting is prevent naturally. So now that you've understood the implementation, I'll just go through the implementation once more so that slowly. Yeah, so you use an accuracy metric called confusion matrix to find the accuracy. Right. So there are certain similarities, as you can note, between bagging and boosting. Both of them use randomly generated samples from the dataset, and the final decisions is made by averaging the results, that is weighted averaging in the case of boosting, or by majority voting in case of bagging. And then there are some differences as well. In bagging, you can see that each decision tree is built differently. Like it does not depend on the other decision trees. There are some 100 decision trees. They take the input, process the output, and that's it. You choose the majority output. Whereas in boosting, each subsequent stump or small tree is constructed based on the output of the previous tree. So it is and the next line you can see that in bagging the classifiers basically means estimators, they are trained parallelly, whereas in boosting classifiers are trained sequentially. And I hope you all understand how that was done. And you can see that each model receives equal weight in bagging, that is basically majority voting. When the weights are same, you just choose what occurs the highest number of times. However, in boosting, the weights are constantly adjusted and normalized based on the results of the previous model. And you know that when the error is lesser for each classifier, you increase the weight in the final model. I hope this was clear and you can understand a broader application of decision trees. Like all of these use decision trees. Yash explained. But you can see how decision trees, when combined with each other in different ways, lead to very powerful models that can be used for a variety of purposes. And these ensembling methods are probably one of the most widely used machine learning techniques. So I hope this session gave you some clarity. And there are some more applications based on these two topics, which Saran will explain. I'll give it to Saran. Yeah, if there are any doubts before I end this section, please post it in the chat or ask me.
Shankar, there are two questions in chat.
Yeah, go on. Oh, okay, 1 second. I'll open the chat. Right. If there are a large number of incorrect terms, then would it not lead to greater error in the final model? Yes, that is correct. When there are incorrect stumps, there will be a higher error in the model, but we will try to decrease the error by reducing the weight of those stumps in the final model. Say there are like 3 stumps with a bad output, and then there is 1 stump with a good output. We will proportionally give the weight, as in um, the first stump will have like probably 3 times the weight of each of those wrong samples, so that it is treated more well in the final model. It has more weight in the final model. So whichever stump gives the correct output based on our training, that will have more say in the final model. But yes, you are correct. When there are larger number of incorrect stumps, the error will obviously increase. But you can say that the weight of those stumps will also decrease. So yeah, you'll have to find out the exact error. Is ADA boost used ANN? ANN? What is ANN?
Okay, so I mean,
Mahendra.
ANNs are artificial neural networks. No, ADA boost is
Oh,
not
okay.
in ANNs. ANNs use linear networks.
Yeah. Okay. Yeah, okay then. So if there are no more questions, then I'll hand it over to Saran.
By
No
the
more
way,
questions?
take like a short break. Maybe we'll resume at 4 p.m.
Yeah, sure.
Okay, yeah.
Today stop sharing or like fine.
Yeah, maybe you can stop sharing and Saran can set it up.
Yeah, okay. Okay, guys, thank you. Saran will take over from now.
Sharon, I think you can start now. Sharon, I'm not sure you're audible. Maybe check. Are you speaking anything? Maybe can you log out and log in again? I think that might resolve the problem.
Am I audible now?
Yes, Sharon, you are audible now.
Yes.
Okay. Yeah, I'm sharing my screen. Like, can you confirm if it's visible?
Yeah, it is visible.
Okay. Okay, so I'll get started.
Okay.
Okay, so hi everyone, I'm Saran. I belong to the CS21 batch. And in today's session, I'll be giving you an idea of how recommendation systems work, the intuition behind them, and two of the most common models that are being used today. So you can see the logos of these three companies here, Netflix, Amazon, and YouTube. Like all these three major companies have recommendation systems as the core of their marketing strategy. So example, when you log into Netflix, you see the first thing that you see is a list of recommended movies. So the reason that they do is because they want to guide the users and not make them feel lost. So this basically increases engagement, and the users use a platform for a longer time, so which contributes to their profits. And if you take Amazon for example, when you buy a product, immediately below you see a list of recommended products. So you're more likely to buy those recommended products also. So say you buy a book, you'll be recommended its sequels, right? You'll be recommended a proper a very clever set of recommendations which will make it highly likely that you buy it also. So you can clearly see the recommendation systems are very crucial to all these major companies. So in today's session, I'll be giving you an idea of how those work. So yeah, let me move to my collab file. Yeah. So recommender systems are designed to recommend things to the user based on a variety of factors. And these systems predict the most likely product that the users are likely to purchase and or of interest to. And how is this related to machine learning? Well, recommendation systems are like form a subclass of machine learning. So if you want to convert recommendation systems like to a problem statement in machine learning, it would be like something like this. So it's a system which predicts ratings a user might give to a specific item even before the user has interacted with the item. So and these predictions, so there are a set of items that the user has bought, that is fine, and the user has rated it maybe. So you have this data, and what you want to do is you want to take the list of items that the user has not interacted with yet, and you want to predict how the user might interact with it, whether he will like it or not. So this is the problem statement, the machine learning problem statement of this recommendation systems. So before we dive in, I'll just go through some of the terminology involved that we'll be using below. So the first thing is items. So an item is basically an entity that a system recommends. So suppose you take Google Play Store, for example. There the item is the app, right? So you get recommendations for apps that you might want to install. And for YouTube, the items are videos. So your recommended videos, essentially. And the next terminology is query. The query is basically the information that a system uses to make recommendations. So yeah, if you take a app store for the Google Play Store, for example, the information that is used is basically the most basic information that is used is the apps that the user has previously installed already, right? So that is one information. And also, if you take Google, it's a large corporation and it also has a search engine. So it really uses this also. So it also uses the keywords that you have searched on the search engine to make uh, uh, to make predictions as to what app you might want to install, and it gives recommendations uh, based on the keywords also. Similarly, YouTube, all these are companies under Google, so they obviously use as much data that they have. So they're going to use keywords that you use in the search engine to recommend videos to you also. So you can see here the ID of the user. This is basically the Gmail ID that you use to access all these services. So this is used, and the items that the users have previously interacted with, all those apps that you've installed in the past. And now the third terminology, and this is an important one, is called an embedding. So the technical definition of an embedding is basically it's a mapping from a discrete set to a vector space. So this is like very technical, but basically what it means is you describe things like objects in a daily life, like a movie, a book, or a commodity. Example, a pen. Example, you describe these objects as a bunch of numbers. So you might think, how is that possible? That doesn't make sense. Well, there's a clever way in which you write these objects as a bunch of numbers, and the bunch of numbers is basically called a vector, right? So we'll as we move down, I'll tell you how these objects are actually converted to numbers in a proper way. So yeah, and many recommendation systems rely on having a appropriate embedding representation of the queries and items. So embedding is actually a central part of these recommendation systems, or even in natural language processing. So in natural language processing, each word is converted to a bunch of numbers based on their context in the sentence and so on. So all these are called embeddings. You convert something to a bunch of numbers, and that bunch of numbers is basically your vector. So recommendation systems are broadly classified into two different types. The first one is content based recommenders. Okay, before I move, like, does anyone of you have any doubt until this part? Okay, if you have any doubt, you can interrupt me in the middle. Okay. Okay, so I'm moving on to content based recommenders. So in content based filtering or recommendation, what happens is you use item features to recommend other items similar to what the user likes already. So example, you consider the same example as an app store. So I have a figure here. So what it shows is this app here. Like there are three apps and there's a user. So I've used a term called item features. What does it mean? An item feature basically are the features of the items. Here the items are applications, right? Each app is an item. And you can see there are just six texts on the top. Each of these like is a feature of the item. So an app can have a feature education. Does it belong to the education category or not? Does it belong to, is it for casual use? Is it for related to health? And these three are publishers. These can also be features for an app, right? Features are basically that describe these items. So all these three are just companies or publishers of these apps. So yeah, and in this example, what I'm to simplify it, what I'm doing is I'm just considering it as a binary system. So an item can either have a feature. If it has the feature, it's just labeled 1. If it does not have the feature, it's 0. So here, this app here is a part of education. It's an educational app. So I just represent it as 1 here, right? And it does not belong to casual. It does not belong to health. So just 0, 0 here. And same, it's published by Science RS, that company. So it has a 1 here and it has a 0 here. So, but this need not be the case. You can also have decimal. Like an app can also be educational, can also be health, can also be under health category. So you can maybe, you could give some decimal values. Like education can be 0.5, health can be 0.5. Education can be 0.3, health can be 0.7. So this is actually possible in the practical case. That's what's done. Binary is not that much used, but for simplicity we can assume, we are assuming it's of binary type. So, and it seems kind of intuitive, like if you have an app, you can classify it as education, you can classify it into these features, right? The publisher does that for us. So when you go to the app store, when you click on education apps, you see a list of apps. It's already labeled into these features. But now what we want to do is we are representing the user. Suppose we are taking a single user. We can also represent the user in the same feature space. Feature space is basically this space here. Like there are the apps on the left hand side and their features on the top. So now this is quite natural, like representing the apps and the features. But how do we classify the features of a user? So we place the user in this space. So how do we decide education, or how does it work? So how that works is it's based on preferences or feedback. So the feedbacks are of two types: implicit and explicit. Implicit is basically like, suppose this user has installed a bunch of apps in the past. Okay, he has not given any ratings specifically like 1 to 5 for these apps. He has just downloaded these apps in the past, and that implicitly tells us that he's interested in these apps. That's why he downloaded, right? So what we can do is look at the list of apps that he has downloaded already, and in this case, yeah. So suppose he has installed another app in the past that has already been published, that has been published by Science RS company. Like this company has published a bunch of apps, and our user has downloaded an app from the publisher. So we can safely assume that the user is kind of interested in the apps that are offered by Science RS. That is one data point that we have received. Another can be healthcare too. Maybe the user has downloaded an app from healthcare too. So these belong to implicit feedback. The user has not explicitly given rating to them, but we are just implicitly assuming that the user might be interested on this based on because he has previously installed apps from this company. Now, what is explicit feedback? That is basically the rating. Suppose our user has rated some apps very well. Suppose he has rated healthcare 5. So we add that, we put a 1 here corresponding to our user because he's interested in healthcare apps. We can assume that. Now, and education, and maybe another form of explicit feedback could be he has, while searching for apps, he has searched, I want to look for education apps. That is direct, right? He's searching for education apps. So obviously you want to put it there. So yeah, these are basically the two types of feedback, implicit and explicit. And we construct the embedding for a user in this feature space. So our embedding in this case is just like, you can call it 1. There's no casual thing here. So 0, 0, 0, and 1, 1. So you can notice that we've already come up with an embedding for each app, and using feedback, we have developed an embedding for the user as well. So now the main task, we have to do the main task now. That is which app, and note that these three apps haven't been downloaded by the user yet, right? So these three apps, he's looking at it for the first time. So what we want to do is we need to create a model that recommends among these three, it recommends some app to the user and which would be the best fit. So now, since we have the embeddings already there, so now the next step is to pick a similarity metric. A similarity metric is basically it's a measurement. It's a system of measurement that to match the user to a particular app. So basically, you're comparing the embedding of the user with embedding of an app, how compatible they are. So the more compatible they are, the more you want to recommend it to the user, right? So now we have the user embeddings. So how do we compare? How do we see if an app is compatible with the user? One obvious thing you might notice is more fields that are common with the app and the user, more likely that the user wants to install that app too, right? So you can see the first app has two fields that are in common with the user. The second one has no fields that are common with the user's preference. So you don't want to be recommending that, obviously. And the last one has one field that isn't common. So an obvious choice might be to recommend app one, and that is correct. But what is the mathematical proper way to for the computer to do this automatically? Let's see. So first, here is a picture, the vector representation of the embedding of app one. This is app one, the chemistry kind of thing. So you can see here that I've labeled it, I've called it A1. So app one, and it's the embedding of it. You can see in education, there's a one there because it falls under the education category. Casual and health is zero. Similarly, zero here. And time waster, I mean, that is a company's name. There's a zero there as well. Science are as one, healthcare zero, right? So this is basically a column vector. So what you've done now is you've taken the app, which is here, and you've converted it to a bunch of numbers. So this is your embedding for app one. Similarly, you find an embedding for the user as well, based on his preferences that we've already marked here. So similarly, this is the embedding of the user. There's 1, 0, 0, 0, 1, 1. And notice that the dimensions, like this is a 6 cross 1 vector, even this is 6 cross 1 vector, are the same because they belong in the same feature space. There are 6 features. The apps also belong to this space and the user also belongs to this space. So the dimensions match. So now the computer somehow extracts these embeddings based on this feedback this thing is called a feedback matrix. Like there are dots, there are one, where there's no dot there is zero. So the computer can easily extract this two embeddings from our feedback matrix. Now how do you tell the computer how to compare a user and an app mathematically? So a simple similarity metric that can be used is a dot product. So many of you might have heard of dot product, like a dot product of vectors. That's exactly what we're going to be doing now. So once you pick a similarity metric, then you must set up a system to score each candidate according to that similarity metric. And note that here we just have one user. There are no other users' opinions matter to this user's recommendation, right? That is a property of content-based recommenders. So let's see how we are doing the dot product and giving it a score for each app. So what we do is, so the question is in the above example, which app should be recommended to the user? So what you do is you do this operation called dot product. So there's just these angular brackets, which is technically this is a symbol of an inner product, but an inner product is just a generalization of a dot product. So it doesn't matter. We can just call this as dot product. So what we do is the first parameter is the user's embedding here, and the second parameter is the app's embedding. And the definition of this operation is to take the transpose of U matrix, multiply it with the matrix, multiply it with the embedding of app1. So a transpose is basically you take U embedding here, that's here. This is a 6x1 column vector. So when you transpose it, it basically becomes a row vector. 1 is here, 0 goes here, the other 0 goes here, and so on. So you can see I've just flipped it 90-degree anti-clockwise. So 1 0 0 0 1 1. So this thing is U transpose, and A1 is just the embedding of app1 that I've just written it as a column vector 1 0 0 0 1 0. And now this is just and now what you do is just matrix multiply. So you take the first element here, multiply with the first element here. 1, you get a 1 here. 0 with the 0, there's no 0, and that's it. Just continue doing that, sum of the elements, and you get the value as 2. So now this 2, like what does this 2 mean? This 2 is basically the similarity score, right? So now for app1 we get a score of 2, and we already saw that this 2, what it basically means here is the number of common fields between app and the user, right? Because we have used a binary system. So this matrix, this whole dot product basically is finding the number of common fields between the user and the app1. And it's clearly 2, but we got it mathematically. Now, similarly, we can do this for app2 and the user. So if you do the dot product of app2 and the user, you will get a score of 0 because there's no common fields. And app3 and the user, you'll get a score of 1. So clearly, the one which has a higher score would be recommended to the user. So in our case, in this example, app1 will be recommended to the user. So this was an example of content-based recommending. So what you do is you split. Okay, let me come to the advantages while explaining. Yeah. So the advantage of this method is that you don't need any data about other users, right? So you just need features, a set of features to describe your data, and you just need your user's preference and the app under what feature it falls, and you'll be able to determine what app needs to be recommended. You don't need the data of any other users. So that is one advantage. So you can scale it to an arbitrarily large number of users, any number of users you want. The second advantage is that it captures a specific interest of a user. So now suppose this user had some preferences. Okay, suppose this user liked a specific downloaded an app from example time waster example. So this user has downloaded an app from time waster, but no other user on the planet has downloaded an app from that publisher. So but still there is a probability, there is high probability that some app published by this company will be recommended to this user because he has downloaded apps from them in the past. So you can clearly see that the recommendation is very niche, right? So this user, only this user is interested in a particular publisher's apps, and it's being recommended to them, and not it's not being dependent on how popular it is with other people. It's very niche, and so it gives them a very good recommendation of apps, like tailor made for the user. Okay, but along with this comes some disadvantages. First, the first thing that we did was we looked at some features. So where do the features come from? All these features like education, casual, health, these are all handmade, right? If you have an app store, these features are handmade and already built in by developers. Like it doesn't automatically know that these are the features. So we need to be able to like develop these features and then create embeddings for each app. So this means that we need to have knowledge in the domain. So in apps, I need to know that I can like classify apps into this category: education, casual, health. So I need to make these features myself first. So a lot of domain knowledge is needed for apps. Okay, it's simple. For movies also, you can do the same thing. But then obviously for movies, you need to know the different genres of films. So you need to have knowledge of the domain. So that is one disadvantage. So the model can only be good as the hand engineered features. So you make good features, you'll get a better model of recommendation. And if the features aren't good, similarly, your model's predicting power comes down. And the other disadvantage with this content-based recommendation system is, clearly, you can see this because it recommends apps, it recommends new apps which are like similar to the user's existing interest. So suppose the user has downloaded an app from Science RS before, they get recommendations from for other apps published by the same company, right? So only the recommendations are like a subset of the user's existing interests. So it doesn't care about what the user might like in the future. Suppose the user develops a new interest, so it doesn't care about that. It just takes the existing interest and just extends upon it, like gives recommendations as an extension to the existing interest. So that is one disadvantage of this feature. So it has limited ability to expand beyond the user's existing interest. So yeah, that covers content-based recommending systems. Like, any doubt until now? If you have any doubt, you can post in the chat or unmute. Okay, so I'll move on to the next set of recommenders, the next category of recommenders, that is collaborative recommenders. Now, this is more powerful, and this addresses some of the limitations of the previous content-based filtering system. So what it does is, like, this scenario is possible. So an item can be recommended to user A based on the interest of another user B. And the other user, I've written a word here, similar. So if a user, I will define how users can be similar, but based on interest of another person, you get apps recommended. So this is like in contrast to the previous set of recommenders that we look where the other users didn't even matter. You just take a single user, just extend upon his existing interests. But in this one, you also need the data about other users. And the major advantage of this method is the embeddings can be learned automatically. So the embeddings of each user can be learned automatically without you mentioning them. User or the items, example, the movies, apps, these embeddings can be learned automatically using certain algorithms, which I'll mention below. So to understand collaborative recommenders, let me take an example of a movie recommending system. So now you can see here, this is our data. So, and here in this example, I've considered a 2D embedding model. What that means is each item is described by two features. So if you go back to the previous one, you can consider this to be a 6D embedding model. Like each item or each item is described by 6 features, right? So in this one, for collaborative recommenders, the example I'm considering just a 2D embedding model for simplicity. But the embedding space can also be of higher dimensions. It can also be more than 2D, 3D, 4D, even 10D, even 50D is possible. But for simplicity, we're assuming this. So I'm considering the two features to be, first, the audience for which the film is meant. So it can be towards children, like more inclined towards children, or more towards a mature audience, adult. And the second feature is, was its performance in the box office? Was it a blockbuster? So blockbuster essentially means it's meant for a wide audience, right? And art house, that means it's just for a very niche set of audience, very limited set of audience, the film is meant. So these are the two features that I'll use to describe all the films that are here and the audience preference as well. You can see here there are 1, 2, 3, 4. There are 5 films and there are 4 users or audience. So let's see how we create a feedback matrix for this data set. Now what we do is similarly create a data set, put the audience on the left hand side and the movies on the top. And suppose this thing is given, like if an audience has watched a particular movie, the corresponding cell in this matrix is given a tick. So this guy has watched this movie, these 3 movies. Uh, she has watched these 2 films. She has watched these 3 films, and she has watched these 2 films. So this data is already there with us, right? So if you take a look, if you look at Netflix, they already have this data of what films you have already viewed. So now what you want to do is, you see this red box here with a question mark. Our task is to just check if the movie Shrek should be recommended to this person or not. So that is our task. So first, let's see what to do. Now first, now you can see this space here. So on the x-axis, children to adult. Like if a film is meant only for children, like mostly for children, its score is -1. Maximum score is -1. And as you increase from -1 and so on, the movie is meant for adults. So that is the scale on the x-axis. On the y-axis, similarly, if it says if a film is very it belongs to the art house class, that is, it's meant for a very niche audience, it's given a score -1. And as you increase from -1 to 1, it means the movie is meant for a wider audience and has performed well at the box office. And you can see that here, each film, or each of the 5 films, actually plotted on this graph. You can see this film is not specifically meant for children, but yeah, like more towards children, and it's very art house. And Shrek, it was a blockbuster and also meant for children. Harry Potter, again, can be watched by both children and adults. Sort of, if you look at film certification, our film certification board India would rate it UA probably. So these films are more U, these films are UA, this is A, something like that. And you can see this, The Dark Knight, it's more towards mature audience, and again, it's a blockbuster. And Memento is the opposite. Not exactly opposite. It's meant for adults and has a very niche audience. And you can see here that again, here too I've plotted. I know the embeddings of the movies, and here again, for the sake of simplicity, for each user, I've already plotted them on this feature space. Like for this woman, I've given a rating of around her preference. You can see here it is 1. So that means she wants to watch more mature audience based films. So it's given 1 here. So this column basically talks about the first x-axis. What are their preference? So this woman has a preference as -1. That means she wants to watch more uh, movies made for children. And this woman here, it's common. She doesn't matter. She wants to watch movies meant for both. And this person here has a rating 0.1. So he's just like, wait, yeah, 0.1 is just to the right of the y-axis. So again, he's almost the same, similar to this woman here. So I've written the embedding values for the first feature, like beside them. And the second feature is, do they want to watch blockbuster or more art house films? And again, I've given the corresponding scores here. So a -1 indicates they want to watch more art house films, and a 1 here, that indicates he wants to watch blockbuster or films meant for wide audience. So here now finally I've represented our embeddings of our audience here. Now I mentioned that you can actually learn the embeddings of the users. right? But here, for sake of simplicity, I've assumed we have already used an algorithm that I'll mention below, and I've received the embeddings of the users and the embeddings of the film as well, right? So again, I have the embeddings of all the users as well as the films. So my next task is just predicting uh, whether I should recommend the movie Shrek to this person or not. So it's the same. Now I use the same similarity metric, that is again use dot product, right? So what I do is I take the embedding of the user. So here, let me see. Okay, let's first consider the embedding of the movie Shrek. Let's keep -1 as the first feature, 1 as the second feature. Like the first feature is whether the film is meant for children or adult, and the second feature is it art house or more blockbuster, right? So, and what I do is, just to give you a sense of scale, let me consider a hypothetical user whose embedding is exact same as that of the embedding of the movie
Karan,
Shrek. Yeah.
sorry to stop you. We are like over time already. Maybe try to wrap it up in like 5 minutes.
Oh, okay. Yeah. So I take the embedding of movie Shrek, which is -1, 1, and I consider a hypothetical user whose embedding is -1 and 1, right? So obviously this movie is perfect for them to watch. So you can see if I take the dot product of these two, I get a score of 2. And you can obviously imagine that this will be the maximum score that can be achieved by any user. So if you get a score of 2, that means this movie will surely be recommended to you. Now let's take the user, this user, let's take her user embedding, which is 1 and 0.1 below, right? This is the embedding of the user, and this is the embedding of the movie, -1, 1, Shrek. And if you calculate the dot product, you get -0.9. So this will give you a sense of scale, whether you should recommend the movie to the user or not. So -0.9 and 2, to be specific, you need to set a particular cutoff score. So if I have a score above zero point 0.2, I'll recommend it to the user or I won't. So after you set such a score, you'll be able to decide whether I should recommend this movie or not. So this is the basic logic. Now, this diagram basically shows you, like here in this example, I've shown that I already know the embeddings of these items, right? But your data set in actual life, in real life, will be like this. You just know the users, you know the movies, and you know whether you have watched them or not. And there you need to be able to find the embeddings automatically. So there are algorithms for this, and you can see what it does. Like it takes this data and it converts it to something like this: a set of user embeddings and a set of movie embeddings, and each of these cell basically is the cross product of the row and the cross product. I mean, sorry, the dot product of the row and column. So, and higher the score, it means the movie is more recommended. And you can see here the basic idea, intuition behind that algorithm, which detects this, is if you see a tick there, so obviously you want the score to be higher there, right? So he has already watched the movie and you want the score to be higher. So the model, what it does is it creates an embedding in such a way that the scores at these points are already high. So you can see 0.88, 1.6, 0.38, 1.2. These are all high values. So that is the optimization algorithm that is used to find the embeddings for each of these users as well as the film. And once you know these embeddings, you'll know how to recommend movies, right? A lower score means you don't recommend. If a higher score, you recommend the movie to them. And that is the logic. So yeah. And like the advantages of collaborative method is that we don't need domain knowledge because the embeddings are automatically learned. Like I'll mention what algorithm that is. And the model can help users discover new interests. So suppose in the content-based systems, the recommendations were an extension of the existing interests. But in this model, the model can actually the model can help users discover new interests. So if they take two users with similar viewing pattern, suppose these two users have watched two films in common, and the second user has watched a third film also that this user hasn't watched yet. So that third film will actually be recommended to this user. So you can see that it's collaborative. The user 2's interest is matched with user 1's interest because the viewing pattern is similar. So that is the basic idea of collaborative recommendation systems. But the disadvantage of this is that a major disadvantage of this system is the cold start problem. So what the problem is like when you give this data to the algorithm which is going to find these embeddings, you give it a set of movies, you give it a set of users. But what if a movie hasn't been watched by the population yet? So it's a new movie, it hasn't been watched by any user. Clearly, that can't be included in this feedback matrix anywhere, right? So as a result, you end up not even getting the embedding for that movie. And then obviously that movie can't be recommended to anyone because it's not even a part of this feedback matrix. So that is a problem, right? You want, if a new movie comes, even if no one has watched it, you want people to recommend because no one has watched it yet, you want more people to watch it. So how do we address this problem? There are a bunch of ways to address this problem, which I won't be discussing here because of the time constraint. But you can see this is a major problem. Like new movies, you won't even be able to get an embedding from the algorithm. So there are ways to address this issue. And you can see content-based filtering systems are not prone to this problem because even if a movie is not watched by anyone except a particular user, if a user has like I see, as I told here, if a user has downloaded an app from Time Waster before, even if no other user has downloaded an app from that, the user will be recommended more apps from the same publisher because it doesn't matter about how the other about if the other users have previously installed an app from this publisher or not. The user is still recommended based on his own niche interest. So the content-based filters don't face the problem of cold start. So yeah, these were broadly the two classes of recommendation systems. And I hope you got an understanding of how recommendation systems work. And here I've just given an implementation of recommendation system. And I won't be able to explain this because it involves some math. Like I told you, the algorithm which automatically finds the embeddings given this feedback matrix alone. So it's the algorithm is called SVD, or a singular value decomposition. It's of the matrix. So you take this feedback matrix and apply the algorithm, you'll be able to get these embedding values. But that involves some pretty heavy math. So if you're interested, you can actually go through the code and you'll be able to understand it if you're interested. So you can see here I have I basically have this data set of books. It's basically like a library. So you can see it has many fields: book ID, author ID, genre, reader ID. This is the main thing. So what I want to do, this program does, is it basically like some books have already been read by some users. So it recommends books to a user that a user hasn't read yet. So example, let me take a user with whose ID is 6479. Say, so what I do here, I just type the ID of the user that whom I want to recommend books for them to read. So now if I just run this, program, yeah, you can see that it has recommended. I've passed a parameter how many books it wants to I should recommend, and it has recommended me 5 books. And this SIM is basically a class that I've created. It's called a similarity score. You can see the score is the highest for this book ID, and it decreases as you go down. So these are the 5 top books that are most similar to the preferences of the reader whose ID is 6479. So you can go through this program, and it uses that method of SVD, which involves a bit of math. So yeah, if you're interested, you can go through this. And that's it. And that pretty much covers this topic. So if you have any doubts, you can ask. No. Okay, no one has any doubts. So yeah, Ashish, I'll stop the meeting.
Yeah, okay, sure.